Hey guys, Professor Brown here, and this is the presentation for Chapter 9, which deals with the topic of thermochemistry. Thermochemistry is the study of the energy changes associated with chemical reactions. As you can see from the picture here on our title slide, we have a very energetic chemical reaction taking place, and we have lots of ways that we can measure the energy change either released or absorbed when chemical reactions take place, and we will investigate a few of those as we move through Chapter 9. Before talking about the energy of chemical reactions, we will stop and take a moment to remind ourselves of what exactly energy is and how we categorize energy. Energy is defined in science as the capacity to supply heat or do work. One of the broader schemes of energy definitions categorize all types of energy as one of two types, and they can either be potential energy or kinetic energy. Potential energy is the energy an object or a system has due to its position or its composition or its condition. The classic examples of potential energy are things that are suspended above um, the ground or something that's gone up a hill and it has the potential to roll back down that hill or fall back down to earth due to gravity. When it does so, it would convert its energy into kinetic energy, which is what we typically perceive as the energy of motion and the energy that things have when they are in motion. And so your classic example of the ball rolling down the hill has potential energy at the top of the hill that is converted into kinetic energy as it moves down the hill. As it comes to chemical equations, as it comes to chemistry and chemical equations, potential energy is generally thought of as the energy stored in chemical bonds. When atoms bond, they use some energy or release some energy as they form those bonds, and that's typically how we perceive chemical potential energy. Kinetic energy, as it attains to chemistry and chemical reactions, is the energy that is associated when molecules move or expand during a reaction. And we actually see an example there on the picture that we see on our slide there. So there is chemical energy stored in the bonds of the hydrogen and oxygen molecules that make up the fuel of the rocket. A source of ignition provides a spark that allows some of that energy to start being released. And as those bonds break, they provide energy to the molecules beside them. And all of that chemical potential energy stored in the bonds of that fuel starts to be liberated. When it does, two things happen. We can see a lot of heat. A lot of heat is produced, but also those molecules burst and move and expand. And that's actually what pushes the rocket forward. So we can perceive both types of energy, the two broad potential energy and kinetic energy definitions within a chemical reaction. The other type of kinetic energy that we normally associate with molecules and atoms is that of thermal energy. All molecules and atoms, according to the kinetic molecular theory of matter, have random vibratory or rocking and shifting and moving and shaking type motions. We typically associate that with temperature. When we say something feels hot, that means that its molecules and or atoms are shaking and moving really quickly. When we say something is cold, that generally means that those molecules and atoms don't have as much thermal energy. They don't have as much vibration or shaking action to them. You can see, I think this is a really cool macro demonstration of this phenomenon there. As we drop dye into hot water and cold water, the much more energetic vibrations and motions of the molecules of water that are hot spread those other dye molecules out a lot faster. Where in the cold jar, we see that a lot of the dye sinks to the bottom without even being perturbed by the water very much at all, because those water molecules in that cold water have much less kinetic energy. They're not moving and shaking very much, so they don't bump into the dye molecules and spread them out like the hot water does. Of course, temperature can be measured quantitatively, and it tells us kind of on average how much kinetic energy the molecules of that sample have. But we typically, it can be kind of a qualitative thing too. So things that are cold don't have as much thermal energy, and things that are hot or warm do have more thermal energy. As with a lot of properties across chemistry and science, we have a tough time measuring directly how much thermal energy a sample has. It's very dynamic, and you would have to discretely measure it, you would have to be able to measure the motions of all of those individual molecules. So perhaps more easily measured is a quantity that we commonly call heat, and that is the transfer of thermal energy between two systems or between two compounds. And thermal or heat is measured in joules, as all energy is typically measured in the SI system. One important note or an important factor of this is that heat always flows from the hot system or object to the cold system or object. So as we see in the diagram here, if you have two collections of molecules at different temperatures and you bring them together into contact with each other, those two systems will equilibrate. Some of that thermal energy will flow from the hotter system to the cooler system spontaneously. It's a process that happens, and nothing has to force it to happen. If they touch each other, this will happen spontaneously. As long as the two objects are left in contact, the heat flows from the hot object to the cold object until a point at which they both have the same amount of thermal energy, and at that point they would essentially be at the same temperature. This is the phenomenon we would notice if we left our hot morning cup of coffee out on our desk in contact with the air molecules in the room that are around it. Eventually, no matter how well insulated our coffee cup is, it will reach equilibrium and become the same temperature as the room. So to describe heat exchanges between different systems or different objects, we need to define a few variables. The first that we have on our slide here is a quantity we call heat capacity. So heat capacity is the quantity of heat absorbed or released when an object experiences a temperature change. So what it does is it relates how much energy is required to have a temperature change in an object. So we can say something like it takes 10 joules of energy to heat up 2 grams of water, and that's just an approximation, but that's what a heat capacity sounds like. It tells us how hard or easy it is to warm an object up. A lot of times that can be a useful figure, but perhaps more useful is to know whether or how a material acts regardless of its size. And so we very often normalize heat capacity of objects to specific heat capacities of what the material is made of. So the specific heat capacity is the quantity of heat or absorbed release when exactly 1 gram of a material undergoes a temperature change of 1 degree Celsius. We have the example of the 2 frying pans on the hot plates up above. They are both cast iron frying pans, so these are made of elemental iron. The only atoms in the samples would be the Fe atoms that we see on the periodic table. And so if we're talking about just the plain heat capacity, that's how much heat is required or how much energy is required to heat these frying pans up. One is obviously bigger than the other one. It has more mass, and just from probably everyday experience, you know, it's going to be harder to heat up. If you put each of those pans on your stove and turn the eyes on to the same temperature, as long as your eyes are pretty comparable, then the smaller one is going to get hotter quicker than the bigger one is because it has a smaller heat capacity. However, if we normalize that to mass, they both would require the same amount of energy per gram to heat up. And that's because they're both made of the same material. And iron has a constant amount of energy that is required to heat it up. And so that is the difference between the heat capacity and the specific heat capacity. We typically tend to use the specific heat capacity in chemical evaluations much more than a heat capacity figure. We will do some calculations determining the heat transfer between different processes on the next couple of slides, but I will mention here that when you are asked to solve problems of this manner, you are typically given either the specific heat of the material directly in the problem, or you may be asked to consult a table of specific heats. And there are lots of thermochemical data in big published reports that tell us different properties of common materials. And so this is where we would go and look for the specific heats. Something people have reported over and over again, they've measured because people need these figures to do different calculations in chemistry. And so we would go consult our reference material, or you would be given a reference material to determine the specific heats of common substances with which we can use to determine energy changes of different processes. Any science with the name thermo in it wouldn't be complete without doing some math. And so here we have our first equation for thermochemistry, and the equation says here that for a material heating or cooling, the amount of heat energy, Q, released or absorbed is given by the equation Q equals C times M times delta T, where Q is the heat energy in joules, C is the specific heat of the substance, the units on that are joules per gram degrees Celsius. As we've said, that's what the specific heat tells us, how much energy, joules, is required to heat 1 gram per 1 degree Celsius. And that's how we get the unit that we have there. Mass is measured in grams, as is typical for the SI system. And as always, delta T means we're finding a difference in something. In this particular instance, difference in temperature. We always find deltas or differences by subtracting our final value from our initial value. So TF minus TI is equal to delta T, and that is, of course, measured in degrees Celsius because C also has the units degrees Celsius. So here on this slide, we have our first examples of how to use the heat equation to determine the heat lost or absorbed during a process. Our first example here says how much heat is absorbed when 361 grams of iron is heated from negative 0.6 to 109.3 degrees Celsius. So we're heating a 361 gram piece of iron, a pretty good bit, 110 degrees or so, and we want to know how much energy that requires. And so we use our heat equation that says Q equals C, specific heat, times M times delta T, as we saw on the previous slide. We are asked to solve for heat, so we're solving for Q in this problem. If we say Q equals, they give us here in the problem 0.449 joules per gram degree Celsius as the specific heat, 0.449 joules per gram degree Celsius, times the mass. They tell us our chunk of iron has a mass of 361 grams. And they tell us that the total temperature change goes from negative 0.6 to 109.3. So 109.3 minus negative 0.6 would be delta T. I'll go ahead and make that a plus a positive. And now this becomes just a function of punching the result in the calculator. We see that the We see 0.449 times 361 times 109.3 plus 0.6. Close that parentheses up. And the result I arrive at is approximately 17,813 joules. 17,813.58 joules of energy required to heat that mass of iron by about 110 degrees. The next example here says a piece of unknown metal weighs 348 grams. When the metal absorbs 6.64 kilojoules of heat, its temperature increases from 22.4 to 43.6 degrees. Determine the specific heat of this metal. That could provide a clue to its identity, it says. Maybe we have an unknown piece of metal and we decide to measure the specific heat to see if we can determine what it is. Maybe we have a new material and we want to define that specific heat so others can see it. They might look at your material and say, hey, that would be a good material to insulate something, or that would be a good material to heat things in based on your specific heat reporting. So we are going to try to figure out the specific heat of this material. We have a formula for it. We have Q equals M times C times delta T. I guess I wrote that a little bit backwards. C M delta T. Multiplication doesn't matter, the order. And so, and they give us some of those clues. They don't give us C here, but they do give us, the heat required, they give us the mass, and they give us the temperature change. I'm going to go ahead and rearrange my formula so I can solve for C directly by just plugging in the values they do give me. Rearranging Q equals M times C times delta T to equal C will involve dividing both sides by M delta T. M delta T. Cancel, cancel. C equals Q divided by M delta T. That's a weird looking Q. We'll fix it a little bit, but it'll just be worse. All right, so we can see that if we put Q and divide it by the mass times the change in temperature, that should tell us the specific heat capacity of our material. So C equals, we take a step back here, notice that our 6,000 or 6.64 kilojoules is not quite in the right unit. These equations are rated for joules, so we want to make sure that all of our units match. 6.64 kilojoules is equal to 6,640 joules, because we know that a kilo of anything has 1,000 of that thing. So 6.64 times 1,000 is 6,640 joules. Divided by the mass that they give us here, which is 348 grams, times that temperature change, which is 43.6 minus 22.4 degrees Celsius. And so if I now punch that expression into my calculator, 6,640 divided by 348 times 43.6 minus 22.4, close those parentheses. Looks like the result is 0.9000. Now, if you go and revisit that thermodynamic table of specific heat capacities that we saw a few slides back, you might not find a metal on that table that matches this value exactly, but what you would see is that aluminum specific heat is approximately 0.897 joules per gram degrees Celsius. And depending on the sensitivity of the instruments that we use to measure, that's probably pretty well within the error of this being a sample of aluminum. But for our specific example, the calculated value was 0.900 joules per gram degrees Celsius. Okay, so our next examples here. This next one sounds a lot like the previous problem we just did. It says a piece of unknown substance weighs 44.7 grams and requires 2110 joules to increase its temperature from 23.2 up to 89.6 degrees Celsius. What is the specific heat capacity of this substance? So we saw the rearranged formula just a few minutes ago, and we saw the rearranged formula back on the one of the first versions of the slides. So we will continue with that, the rearranged version that says the heat capacity, C, is equal to the amount of heat required for the temperature change divided by the mass of the object times the change in temperature. So C is therefore going to be equal to 2110 joules divided by 44.7 grams times 89.6 minus 23.2 degrees Celsius. Get our handy calculator out and we type 2110 divided by 44.7 times, get that decimal in there, 89.6 minus 23.2. When I input all that into the calculator, I arrive at a value of 0.71. So the heat capacity of this material is 0.71 joules per gram degrees Celsius. Now, on to the next example. We see the next one says an aluminum kettle weighs 1.05 kilograms and is at room temperature, which is 20 degrees Celsius. If 5,500 joules of energy is supplied to the kettle, what will the temperature of the kettle rise to? So reading this problem tells me that they're trying to figure out what is the final temperature that you arrive at when you apply a certain amount of heat to a kettle of a given mass. They give us the specific heat of aluminum and to tell us that the kettle is made out of aluminum. So we're solving for one of our temperatures. So if I look at the formula, Q equals mc delta T, we're actually solving for one of the terms inside our delta T there. We're solving for TF. They give us TI. I'm going to rearrange this formula such that I solve for delta T, and then I can expand delta T when I'm ready to finish. So delta T should be equal to Q divided by M times C. If I divide both sides by MC, I'll cancel MC on the side with a delta T and move it over to the side with Q. So the change in temperature is equal to the total mass or the total energy divided by the mass of the substance times its specific heat capacity. So if I put those values in, delta T is equal to 5,500 joules. That's the value they gave us for the amount of energy put in. They tell us it's 1.5 kilograms sample, so we need to convert that to grams. Again, we multiply by 1,000, so that is 1,050 grams. And then the specific heat capacity of aluminum is given to us as 0.897 joules per gram degree Celsius. And so if we punch that into our calculator, if we say 5,500 divided by 1050 times 0.897, then it tells us the temperature change should be about 5.8 degrees. But we need to keep in mind that that is not what the question asked for. The question asked for what is the final temperature. So if temperature change is equal to 5.8 degrees, what that means is Tf minus Ti is equal to 5.8 degrees Celsius. They give us Ti, and we know the temperature starts at 20 degrees. So Tf minus 20 equals 5.8 degrees Celsius. Therefore, Tf must equal 25.8 degrees Celsius. So with 5,500 joules of energy added to our kettle, we were only able to raise the temperature of the kettle by 5.8 degrees, making the final temperature of the kettle 25.8 degrees Celsius. Section 9.2 talks about calorimetry, which is a broad set of methods that scientists, chemists use to study the heat changes or heat transfers for a process. The reason that we have to use special methods to do so, called calorimetry, is because measuring the heat change of chemical reactions may not be as straightforward as it seems on the surface. If we think about trying to measure how much heat energy is lost when something cools off that we don't know the specific heat capacity of, we're trying to measure the amount of energy coming off of a substance. Think about trying to hold a thermometer over a fire that's raging just kind of out to the atmosphere and trying to get an idea of all of the energy coming off with just that thermometer. You can't do it because all that energy is escaping to the outside atmosphere. You're not able to collect it all for measurement. And so in order to circumvent that, we've come up with this process of calorimetry whereby we enclose a system and its surroundings from the outer universal surroundings and measure how much energy is transferred between those two quantities. Typically, the surroundings that we're measuring is a solution, oftentimes water, that we can directly measure the temperature change of. And if we know exactly how much water is there in those surroundings, then we can get an idea of how much energy was released or absorbed by certain processes by just measuring how much temperature change we have in that specific mass of water. Calorimetry calculations are predicated on the following assumptions. When you drop a substance, a heated substance or a cooled substance into water, the heat absorbed or lost by that substance is equal to the heat absorbed or lost by water. You'll notice that they are opposite in sign. What those equations are basically getting at is that if I take a hot piece of metal, that's why it's listed as substance N, often, especially these problems are written as a hot piece of metal is dropped into water, and then the amount of heat or energy lost by the hot piece of metal is equal to the amount of heat or energy gained by the water, and that's why they're equal but opposite in sign, positive and negative, because the amount of energy that one material loses is the amount of material that the other material gains, or vice versa. The same can be said for chemical reactions that are measured in aqueous solutions. We'll see some problems where we mix two components and a reaction happens. Think the and the amount of energy released by those reactions is absorbed by the water that they're in. And so the energy change of the water is equal to the negative energy change of the reaction, and vice versa, because however much energy that reaction let out was the amount of energy absorbed by the water. Also, you can have reactions that require energy to be put in, and that energy had to come from the water, so it would be the amount of energy lost by the water. So again, calorimetry is predicated on the principle that once equilibrium is reached, the amount of energy lost by one material is equal to the amount of energy gained by the other material, indicated by them having opposite signs.
Here we have our first calorimetry example. It says a 360 gram piece of rebar is dropped into 425 milliliters of water at 24 degrees Celsius. The final temperature of the water was measured at 42.7 degrees Celsius. Calculate the initial temperature of the piece of rebar. Assume the specific heat of steel is approximately the same as that for iron, and that all heat transfer occurs between the rebar and the water. There is no heat exchange with the surroundings. Water equals 4.184 joules per gram degree Celsius. Iron equals 0.449 joules per gram degree Celsius. Those are each of the material specific heats. The last sentence there, all heat transfer occurs between the rebar and the water, reminds us that the amount of energy lost or absorbed by the metal is equal to the negative amount of energy lost or absorbed by the water. So in this case, Q of the metal equals negative Q of the water. The metal, Q is C times M times delta T, and that would be all for the metal values. And on this side, we would have C times M times delta T, all for the water values. We'll fill in what we know. C for the iron is 0.449 joules per gram degree Celsius. The mass of the metal is told to be 360 grams. The change in temperature of the metal, we'll figure out. We want to know what temperature the metal started at. That's what we're being asked here. So we don't know the final or the initial temperature of the metal, but we do know the final. Calorimetry is assumed that everything comes to equilibrium. So if the final temperature of the water is 42.7 degrees, the final temperature of the metal is 42.7 degrees. So 42.7 is the TF. We don't know TI. That is what we are going to solve for. Then if we see for the water side, we have to can't forget our negative signs. That's imperative for these calculations. So the negative Q of the water is equal to C, which is 4.184 for water, times the mass of water. They're not given a mass directly. We're told we have 425 milliliters of water, which means we have 425 grams of water, because water is 1 gram per milliliter. So we can put 425 grams down for the mass of the water. And then we do know the entire temperature change of the water. It says the water was initially 24 degrees and it stopped at 42.7 degrees. So delta T for the water is 42.7 minus 24.0. I'm going to simplify a lot of these expressions for myself. I will see that 0.449 times 360 is 161.64 times 42.7 minus T sub I equals, and I'll multiply all of that, 4.184 times 425 times 42.7 minus 24.0. And that gives me a figure of 33,252.34. Now, if I divide both sides by 161.64, I will arrive at the following expression that says that 42.7 minus the initial temperature is equal to 33,252.34 divided by 161.64, 205.72. So 42.7 minus the initial temperature is equal to, and I'm forgetting those negatives. That is all negative. And so therefore, this would be negative. 42.7 minus Ti is equal to negative 205.72. So if I add 42 point, so if I, let's see, if I add 42.7 to both sides, negative Ti is equal to subtract 42.7 from both sides. I will negative 205.72 minus 42.7 is negative 248.42. So I subtracted 42.7 from both sides to arrive at negative Ti equals negative 248.42, which means that positive Ti is equal to positive 248.42 degrees Celsius. So the initial temperature of the metal before it was dropped into the water was 248.42 degrees Celsius.
All right, we have the next example for calorimetry here. It says a piece of metal weighing 59.47 grams was heated to 100 degrees Celsius and then put into 100 milliliters of water, which had a temperature of 23.7 degrees Celsius. And then the metal and water came to the same temperature, determined to be 27.8. Assuming no heat loss to the outside environment, what is the specific heat of the metal that was dropped in the water? And for this example, we again are going to use the fact that the heat lost by the metal is going to be the same as the heat gained by the water. So Q of the metal is equal to negative Q of the water. And then we just set our problems up. Q is equal to Cm delta T. For the metal, we've been asked to find the specific heat. So we don't know what C is. We'll just write C down, maybe C of the metal to be sure. And we're supposed to multiply that by the mass of the metal, 59.047 grams, and the change in temperature of the metal. The metal says it was 100 degrees to start with and then reached a final temperature of 27.8 degrees. So 27.8 degrees Celsius minus 100 degrees Celsius is our change in temperature for the metal, or the change in energy for the metal. And then for the water, we have negative. The specific heat of water is 4.184 joules per gram degree Celsius. The mass of the water here, again, they kind of test our knowledge that 1 milliliter of water has a mass of 1 gram. So 100 milliliters of water is equivalent to 100 grams of water. And then the temperature change in the water was, the final temperature was 27.8 degrees Celsius for the water. And then the initial temperature was 23.7 degrees Celsius for the water. So now we essentially have some algebra left to do. We will want to simplify those expressions using our calculator. So we will say that 59.047 times 27.8 minus 100 equals about negative 4,263. And that is gram degrees Celsius, 0.19 grams times degrees Celsius, because we multiplied the mass and the temperature change together. And we still have our unknown variable there on the outside. Then I will simplify 4.184 times 100 times 27.8 minus 23.7. And the result I arrive at is 1715.44. Don't forget our negative sign, 1715.44. And that is joules. And so we will see that we need to divide both sides by the value that's sitting there with the cm. So we will divide both sides by negative 4263.19 gram degrees Celsius divided by negative 4263.19 grams degrees Celsius. And we see there that our units actually come up to what we want to, joules per gram degree Celsius. So that gives us an indication we're on the right track. When our units work out, we can be pretty certain that we are answering the question correctly. So the specific heat of the metal is approximately equal to 1715 divided by 4263.19. A result of about 0.402 joules per gram degree Celsius. We have another problem here on this slide that says, how much will the temperature of a cup of 180 grams of coffee at 95 grams degrees Celsius be reduced when a 45 gram silver spoon, specific heat of 0.24 joules per gram degree Celsius, at 25 degrees is placed in the coffee and the two are allowed to reach the same temperature. Assume the coffee has the same density and specific heat as water. So this is kind of a neat question because we're putting a cool piece of metal into a hot liquid or hot water essentially in this problem. So instead of the water cooling the metal off, in this case, the metal is cooling the solution off. Regardless, we still operate under the assumption that at the equilibrium temperature, the heat released by the metal is equal to the heat absorbed by the water. And of course, we have to show them with the opposite sign because one released and one absorbed. And so we will calculate the heat released by the metal by taking the, or heat absorbed by the metal, again, in this case, by taking the specific heat times the mass times the change in temperature for all of the metal. Again, we do the specific heat times the mass times the change in temperature for the water as well. Solve for the variable we don't know. In this case, we want to know what temperature they get to, and so we want to know the equilibration temperature in this case. And let's see how that looks when we work it out. So we know that the specific heat of the metal spoon is 0.24 gram degrees Celsius, joules per gram degree Celsius, and it has a mass of 45 grams. And the change in temperature would be the final temperature minus the initial temperature. So we don't know the final temperature. We're asked to find the final temperature for both of these substances, the spoon and the coffee, and we want to keep in mind that the spoon and the coffee will both reach the same temperature, so they both will have the same TF. The initial temperature of the spoon is 25 degrees Celsius. Then we will set that equal to, erase the little typo I made there. We will set that equal to the negative Q of the water. The specific heat of water is 4.184 joules per gram degree Celsius times the mass of the water is 180 grams. And the temperature change of the water is going to be TF minus 95 degrees Celsius, because the water is at 95 degrees Celsius. And we want to know what temperature it gets down to. So I'm going to use the calculator and simplify those expressions down to TF. So I will say that 0.24 times 45 is equal to 10.8. 10.8 times TF minus 25 degrees Celsius is equal to, we are going to do 4.184 times 180, 753. Don't forget our negative sign, 753.12 times TF minus 95 degrees Celsius. All right, now we can divide both sides by 10.8. To simplify the expression even further, 753.12 divided by 10.8 is 69.733. So this will cancel. TF minus 25 degrees Celsius is equal to 69.73, negative 69.73 times TF minus 95 degrees Celsius. Close those parentheses out. At this point, I would probably go ahead and distribute the negative 65, negative 69. So we have TF minus 25 degrees Celsius equals negative 69.73 TF plus and that turns into a plus because of the negative sign in front. It would be minus a negative. So plus 66,624.35. All right. Now we can add 6,000, or we can add 25 to both sides. TF equals negative 69.73 TF plus 66,024.35 plus 25 equals 6,649.35. Now, now we can move negative 6973 over to the other side. That's 1 TF on that side. So when we add 69.73 TF to both sides, we will have 70.73 TF equals 6649.35. Ooh, we finally got our TF down to one last figure. Well, the last thing we need to do is divide 6649.35 by 70.73. And our temperature final should be, grand finale, we have 6649.35 divided by 70.73. 94.01 degrees Celsius. Oh, look at that. Our 45-gram silver spoon only drops the temperature of our coffee by about a degree. Pretty nice because our coffee stays hot. That's really hot coffee, though. That's almost boiling coffee. That's really, really hot. It's like scalded hot coffee. Maybe our spoon should cool it down a little bit more than that. Anyways, this was a really long problem. We'll see you on the next one. Okay, in this problem, we get our first look at reaction calorimetry. So they've told us there's two solutions that we're going to be mixing together. One of them is 0.5 molar HCl, and the other is 0.5 molar NaOH. We have 100 milliliters of both solutions. Both are approximately close to room temperature, 23 degrees, maybe a warm room temperature. And they are mixed together in a coffee cup calorimeter. When the reaction happens, those two, if you remember, they would undergo a neutralization reaction. So the hydrochloric acid and the sodium hydroxide would neutralize each other. Your products would be water and regular table salt, in this case, NaCl. And you would also get some heat produced. This is an exothermic reaction. Some heat is released when this reaction occurs. We know that because when they mix the two solutions together, we see that the temperature climbs from 23 degrees, where they're both at, to about 32.5 degrees. We've got the specific heat of water and the density of water given to us here. Tell us what the approximate heat of this reaction is, so how much heat was released from this reaction. So what we know, again, kind of like we talked about with the metal and the water, when these things come to the equilibrium temperature, we can assume that the amount of water or the amount of energy, heat that was absorbed by that water essentially came from that reaction. So when they ask us for the Q of the reaction, it is going to be equal to the negative Q of the water yet again. And in this case, most of these questions are just going to ask us to find the Q of the reaction and not give us the heat. So we can just write the Q of the reaction, and especially in this case, the Q of the reaction is equal to the negative Q of the water. But we've got a little bit of investigation to do to figure out, well, how do we calculate that Q of the water? We know that Q of the water is C times M times delta T. So the Q of the reaction is equal to negative 4.184 joules per gram degree Celsius times the mass. So we have to think a little critically here. We have 2 cups of this solution, 100 milliliters of each. So when we pour them together, that would be a total of 200 milliliters of water, which is 200 grams of water approximately, times, we are given a temperature change. We know that both solutions are at 23 degrees before they are mixed. Afterwards, they are at 32.5 degrees. So our temperature change is 32.5 degrees Celsius minus 23 degrees Celsius. Now this is just a matter of plug and chug in your calculator. $4.184 times 200 times 32.5 minus 23 equals 7,900, 7,949.6 joules of energy for this reaction. We see that that's a negative number. When heat of reaction is exothermic, we show that with the negative sign. So the negative sign is not out of place here. When a reaction is exothermic and it releases heat, we typically tend to define Q with respect to the system. So if it is releasing heat, the system itself is actually losing heat, and that's the point of the negative sign there. It shows it is lost, negative 7,949.6. I got point joules there, but it's 0.6 joules of heat to the water through the rearrangement of those molecules, through the rearrangement of the atoms and their bonds. Here is another reaction calorimetry example. When 50 grams of 0.2 molar sodium chloride at 24.1 degrees Celsius is added to 100 grams of 0.1 molar AgNO3 silver nitrate at 24.1 degrees Celsius, also in a calorimeter, the temperature of the solution increases to 25.2 degrees Celsius as AgCl or AgCO, silver chloride solid, forms. Assume the specific heat of the solution and products is 4.184 joules per gram degree Celsius, the specific heat of water. Calculate the approximate amount of heat in joules produced. So we are going to determine how much energy is released by this reaction. This one will be set up very much like the one in the previous example, where we have the heat released by the reaction is absorbed by the water, so the Q of the reaction is equal to the negative Q of the water. So if we can figure out the Q of the water, we can figure out the Q of the reaction pretty easily. In this case, the specific heat of water is, as always, 4.184 joules per gram degree Celsius times the mass of the solution. So we see that we mixed a 50-gram solution with a 100-gram solution. So that's a total of 150 grams of solution times the temperature change. We go from 24.1 up to 25.2. So 25.2 minus 24.1 is our temperature change. And again, this is just a matter of punching this one in our calculator. We will say 4.184 times 150 times 25.2 minus 24.1. The result is 690.36. So the heat released by this reaction is 690.36 joules. Here we're going to start section 9.3, where we talk about enthalpy. Enthalpy is the characteristic that most chemists and other sciences use for calculating energy changes in chemical reactions. For the first few slides, we'll talk about what enthalpy is and why we use it, and then we will do some examples of how to manipulate and understand reaction enthalpies. It may come as no surprise if you were listening earlier in the presentation when we talked about energy, that heat energy is not the only type of energy that is expressed or translated during a chemical reaction. We define a figure U as the total energy of a system of molecules, and we say that U is equal to not only just the heat, but also the work done on or by a system on or by its surroundings. So in addition to thermal energy, we also have kinetic type work energies that atoms and molecules participate in. And so to understand the total energy of a chemical reaction, we have to have an idea of how much heat is being released or absorbed, as well as how much work the system is doing. And that's what the total energy of a system describes, is the change in energy according to heat produced or absorbed, as well as work done on or by a system. And you might be thinking, work, well, how do chemical reactions do work? We talked about it a little bit earlier, like I said, way back on the first couple of slides of this presentation, where we take a look at the rocket. When molecules react, they often produce gases that cause expansions, or in some cases, reduce gases that cause contractions. We see an example of it here when baking soda is dropped into vinegar, gas is produced, and that gas did some work there. It blows up the balloon against the pressure of our atmosphere that it's working on. So very often chemical equations and chemical work is interested in expansion work. Expansion work is how internal combustion engines, regular gasoline-powered automobiles and buses and whatnot, get from point A to point B. We ignite fuel, hydrocarbon fuel, gasoline, or diesel inside of the engine, and an expansion happens, and it pushes against the piston, which eventually is translated by a whole set of linkages and gears to rotational motion and rotational energy to propel you forward. So the type of work done by chemical reactions is not always, but in many, many cases, and for the case of general chemistry, the type of work is expansion work, pushing against the environment by the production of gases. Here in this example, we have a diagram that shows the relationship between total energy for a system and how it can either lose that energy or gain more energy. We can see that if work is done on a system, so if something pushes against the system, then the change in energy is greater than zero. Energy is absorbed. Obviously, if heat is put into a system as well, we see right here, this is heat being put into a system, which means also that the change in energy would be greater than zero because the system would absorb heat to gain that energy. And then, of course, if heat is let out, if a system heats its surroundings, then it is losing that energy. That's why delta U would be less than zero. Also, when a reaction or a system of molecules pushes back against the atmosphere by creating gas, usually, we see that the system would do work on the surroundings, and in doing so would lose some of its internal energy. So when things expand, they lose some of their internal energy, not just due to heat, but also due to the work they are doing by pushing against those surroundings. Internal energy is an example of a state function, and this is a good time to stop and explain with an example of what a state function is, because we'll also talk about how enthalpy is a state function and how that helps us to determine the enthalpies and energy changes in unknown or novel reactions. So state functions are any variable, and this holds throughout science. You may hear state functions in your other classes also if you're taking more science somewhere. So it's a worthwhile idea to have a good grasp of. State functions are variables of a system. So they're these characteristics of a system that do not depend on how the system got there. Here's our thought experiment to go with it. Think of yourself as a system, and let's imagine that you just climbed to the top of Mount Kilimanjaro here. Your altitude is one of your functions. We can say the function of system U is whatever the altitude of Mount Kilimanjaro is. And furthermore, it does not matter how or why, what path, in what way you reached the summit of Mount Kilimanjaro. You could have ran straight up in line X and it could have taken you a few hours, Or alternatively, you could have winded around and stopped and camped for days at a time, and maybe it took you 3 weeks to summit Mount Kilimanjaro. Regardless of either scenario, your altitude would be the same. And so therefore, altitude is a state function of system U in this situation. Now, the distance you traveled certainly is not a state function, nor is the time that it required to take you to get there. On path X, we said you ran straight up and didn't stop, and you didn't make any curves or switchbacks or anything. So the length you traveled and the time you took are both short. In path Y, you stopped and camped for days at a time, and you meandered lazily up the mountain, and so the path you took is a lot longer, as well as the time you took. Altitude, however, doesn't care about either of those variables, so altitude is a state function. The other two are not. Internal energy of a system is a state function. It doesn't matter how that system arrived at that temperature. Was it slowly, painstakingly heated up over a couple of days? Or was it placed right in front of a Bunsen burner and heated up in 30 seconds? It doesn't matter, or it wouldn't matter, to the amount of energy. That energy is a state function also. So that brings us to enthalpy. Chemists defined a new state function, enthalpy, by taking the total internal energy of a system and adding to it its current pressure and volume. Regular enthalpy or enthalpy of a system is not really measurable by the instruments that we have, but we can describe the change in enthalpy by saying that the change in enthalpy is equal to the change in the internal energy plus the pressure times the change in volume. Well, it turns out pressure times change in volume is equal to negative W. So when you expand that out, delta, the enthalpy, the change in enthalpy is equal to the change in heat. Remember, U is Q plus W times work plus, well, we just said that P times V is negative work when change. So if a reaction is happening at atmospheric pressure, which is very common in the name of chemistry, we can simply say that the enthalpy is equal to the heat release. So think of this Bunsen burner over here. When it burns, it essentially is not in a container. So it may have a very, very tiny pressure increase effect on the Earth's atmosphere, but it's so small that it's really negligible. So what we're saying is for a reaction at atmospheric pressure, like our Bunsen burner burning here, all of the energy conversion is due to the heat conversion. That makes a lot of our calculations pretty simple. If pressure changes, then enthalpy can also be used, but it becomes a little more complicated and messy. For most of our work, we're going to essentially assume that reactions take place at atmospheric pressure, and therefore the delta H is equal to the amount of heat released by the reaction also. Because of this relationship, we can also say, as with change in Q or change in heat, change in enthalpy greater than 0, a positive figure, would mean that a reaction is endothermic. It is absorbing energy in order to move forward. And change in H that is less than 1, or a negative value, means a reaction is, or a system is exothermic. It means it is giving energy away, usually in the form of heat. We have thermochemical equations to describe the energy changes for these reactions. Thermochemical equations always show the change in enthalpy for 1 mole of product. That's why you see the 1/2 down here in our chemical equations. We haven't seen 1/2s or fractions in chemical equations as of yet. Well, the reason is because in the balanced reaction of this version, H2 plus O2 yields H2O, the balanced version of this says 2H2 plus 1 O2 yields 2 H2O. But in order to show just 1 mole of water being formed, because thermochemical equations show us 1 mole of product being formed and how much energy that releases or absorbs, we had to divide everything by 2. And when you divide Divide that 1 in front of oxygen by 2, and then you get 1/2. So the correct thermochemical equation for the production of water from hydrogen gas and oxygen gas is 1H2 plus 1/2 O2 yields 1H2O. And then we're told that has an energy change of negative 286 kilojoules. So that means there is 286 kilojoules of heat released when hydrogen and oxygen react together to form liquid water at atmospheric pressure. From here on out, every time we see delta H, it's going to kind of look like this, delta H with a little degree sign beside it. When we see symbols with degree signs beside them kind of all throughout chemistry, that usually means it's a standard state measurement or a standard temperature and pressure measurement. It just means that that measurement was made under pretty normal conditions, which usually include things like 1 atmosphere of pressure, 1 molar solutions, 278.15 Kelvin temperature, which is right around room temperature. And there's a few others that may be defined with some terms, but generally just having the degree symbol means it happened at normal conditions. Technically, it's standard state enthalpy or standard temperature and pressure. You may see it written in other areas for other symbols, but then again, it just means that it's under normal conditions. The first enthalpies that we'll talk about are the standard enthalpies of combustion. So these are energy changes that are associated with various combustion reactions, which are when a substance reacts vigorously with oxygen and releases heat, light, and carbon dioxide, usually even some water sometimes. What is typically known as burning or fire. We scientists, have measured different substances' enthalpies of combustion and reported them in various resources over the years. And so we can use these to determine how much energy we're going to get from certain chemical reactions. And of course, burning things is kind of a process that's used to power a lot of our electricity generation, and it's used for locomotion, it's used to heat homes. So there's a lot of vested interest in determining how much energy we're going to get out of our reactants or our materials that are available. And that's what these standard enthalpies of combustion do, is they tell us how much energy we get from reacting these certain chemicals. All right, now we'll take a look at our first example of how we use combustion enthalpy data points. This question here says how much heat is produced by the combustion of 125 grams of acetylene. If we check the previous slide or the thermochemical tables that we have in our text, we see acetylene is one of our entries for the combustion enthalpies. We know that at normal atmospheric pressure with the reaction happening at normal atmospheric pressure, delta H is equal to the Q, the heat of the reaction released. And so therefore, 1 mole of acetylene, according to the thermochemical equation here, 1 mole of acetylene reacting with 5.5 moles or 5/2 moles of oxygen gives us 2 moles of carbon dioxide, 1 mole of liquid water, and 1,301.1 joules of energy released. Now, keep in mind, that's for 1 mole of acetylene according to the thermochemical equation here. So we want to figure out, well, we don't have 1 mole of acetylene, we have 125 grams, which is probably not 1 mole. How much energy is that going to give us? This sounds like a problem for dimensional analysis. If we figure that we have 125 grams of acetylene, C2H2, and we remember that, or we figure out that 1 mole of C2H2 has approximately 26 grams of C2H2. And then we multiply that by the fact that we get 1,301 joules, 0.1, that's 1,301.1 joules of energy released for every mole of C2H5 reacted, or C2H2, excuse me, C2H2 reacted. that cancels grams of C2H2, it cancels moles of C2H2, and it should tell me how many joules I'll get from burning 125 grams of acetylene. So if I pull the calculator up, I will type in 125 times negative 1301.1 times 13.01, that's negative. That's negative 162, 637.5, but I'm going to divide that by 26 grams. And I see that that is approximately negative 6,255.29 joules of energy. So what I did is I took the idea that the thermochemical equation related to me that 1 mole of acetylene gave off 1,301.1 joules of energy. I figured out how many moles 125 grams of acetylene was. Of course, that's more than one since it's 26 grams per mole, so that's approximately 5 moles. And then when you multiply the 1,301 by that approximately 5 moles, you get 6,255.29 joules of energy released for 125 grams of acetylene combusted. We have another example here. It says the combustion of gasoline is a highly exothermic process. Let us determine the amount of heat produced by burning 1 liter of gasoline, assuming the enthalpy of combustion of gasoline is the same as that of isooctane, a common component of gasoline. The density of isooctane is 0.692 grams per milliliter. So this question sounds very much like the last question. We will need to do some conversions to figure out how much isooctane we have there in moles. And then once we know how much isooctane that we have there in moles, we can figure out how much heat is released by the combustion of that isooctane. Because again, we've got another thermochemical equation here rather that relates to us. In fact, we kind of get lucky again. The equation is 1 mole of isooctane plus 25 halves of moles of oxygen gives us 8 moles of CO2 and 9 moles of liquid water, and approximately 5,461 joules of energy. The molecular weight of isooctane is about 114.23 grams per mole. So we're going to note that down here so that we don't forget 114.23 grams per mole for isooctane. So now that we know the molecular weight, we probably have enough information to set up our conversion. So we will say that we have a full liter, 1 liter of isooctane, C8H18. We know that there are 1,000 milliliters in 1 liter of isooctane. We know that the density is 0.692 grams of isooctane per milliliter of isooctane. That's pulled from the problem right there. Then we can see now that would leave us with grams of isooctane. So we want to get rid of the grams and figure out how many moles that is. We would say there are 114 gram, 1 mole of isooctane is approximately 114.23 grams of isooctane. And Now we know that we can see from the problem that 1 mole of isooctane gives us approximately 5,461 joules of energy. There are negative 5,461 joules of energy released when 1 mole of isooctane is combusted, and that will cancel the moles. We can cancel the grams, cancel the milliliters, cancel the liters. And we're left with joules of energy produced by our reaction, which is what we want our answer to be in. So at this point, we just need to plug and chug. We are going to do 1,000 times 0.692 times 0.692 times 5461, 3 million and some change, and divide it by 114.23. I show that that is approximately 33,082.48 joules of energy. 33,082.48 joules of energy released by the combustion of 1 liter of isooctane. Gasoline combustion is a very energetic process, and that's why it's such a good fuel. We also have much data on the standard enthalpies of formation for many common compounds. Formation reactions are reactions that result in a compound made from its constituent elements. So if you took any compound and wrote a formation reaction for it, it would show each individual element in that compound adding up to that compound. The one trick is you have to use the simplest state of those elements, which I'll explain a little bit more in detail in a couple slides. Many of these enthalpy changes have been measured and reported, and that's nice is because we talked about how enthalpy is a standard state, so we can use that information to help us predict the enthalpy changes of reactions we don't know the enthalpy for. And then the standard forms of enthalpy, once again, usually show 1 mole of product being produced. As we're working through these problems, we also want to keep in mind that for evaluating heats of formation, sometimes we will want to flip the reactions around and evaluate it as a decomposition reaction. What would the energy change be if instead of forming the compound, what would it be if that compound broke down into its constituent elements? And when that is the case, just keep in mind, if you reverse a heat of formation reaction, change the sign on the enthalpy change. So these two reactions here, N2 gas plus 3H2 gas yields 2 ammonia molecules of gas, has an enthalpy change of negative 91.8 kilojoules. But in the reverse reaction, they ask us to determine the H for 2 moles of ammonia gas being broken down into 1 mole of nitrogen gas and 3 moles of hydrogen gas. Because this reaction is simply the exact reverse of the reaction above, we can simply say that the delta H for this reaction is 91.8 kilojoules. We have another heat of formation problem here that says 2 moles of boron plus 3 moles of hydrogen yields 1 mole of diboron hexahydride. So, and this reaction actually absorbs heat. Notice there's no negative sign. This is endothermic. It absorbs heat to go forward. Approximately 32.4 kilojoules per mole of diboron hexahydride produced. So we are asked to find the change in enthalpy if 200 grams of hydrogen is consumed during a reaction. This sounds like another one of our conversion style problems. So if we say that 200 grams of hydrogen has approximately 1 mole of hydrogen per 1 gram of hydrogen. That will allow us to cancel grams. And we want to go from moles, and we would be in moles. We want to know how many joules or kilojoules would be the case if we burn 200 grams of hydrogen. Our thermochemical equation tells us that for every 3 moles of hydrogen reacted, 32.4 kilojoules of energy is released. So 32.4 kilojoules per 3 moles of hydrogen released will allow us to cancel out and have our answer in kilojoules. You have to be careful, obviously. I didn't go with just 32.4 kilojoules per mole because that's for the reactant here. There's only 1 mole of reactor or product here. There's only 1 mole of product made. In this reaction, there are 3 moles of hydrogen being consumed. So that means for every 3 moles of hydrogen being consumed, this much energy is being absorbed. So that's why we use 32.4 divided by 3 moles. When we do 200 times 32.4, divided by 3, that lets me know that approximately 2,160 kilojoules of energy are necessary for this reaction to go forward and consume 200 grams of hydrogen. So these formation reactions, again, I want to explain a little bit more in detail. They show the formation of a compound from its free elements in their most standard states. What that means is, like we said, when we write a formation reaction, we break a compound down into its individual elements and we show those being formed. But you have to show, you can't just say that hydrogen or oxygen, for instance, are reacted to form water, because in their most standard state, hydrogen and oxygen exist as H2 and O2 gas. So when you're writing a formation reaction, if you wanted to write the formation reaction from water, you would have to show H2 gas plus O2 gas yields H2O, because that's how oxygen and hydrogen tend to exist. And so you have to pick the state at which an element tends to exist in order to write it into a formation reaction. Luckily, you can determine the standard state for an element by consulting the or a table of thermodynamic properties. The standard state of the element is always listed at the top, and I've got a cutout of the standard thermodynamic properties from our textbook here on this slide. And so I cut the one out. It goes in alphabetical order, and it shows compounds related to aluminum first, because aluminum comes first on the periodic table. But the entry always at the top of each of these elements entries in these standard thermodynamic properties for selected substances is the standard state of that element. So we can see that aluminum's standard state is just solid aluminum, because that's how aluminum tends to exist in the by itself in the on planet Earth here in the universe. And that goes for a lot of your metals. Most of your metals exist as just metallic solids. But again, we have to consult the thermodynamic tables to be certain of what a standard state is for the element we want to write a formation reaction with. We will practice writing our own formation reactions here. The first one says, write the formation reaction for calcium oxide. When we write a formation reaction, we need to figure out a couple of things. We need to figure out what the actual formula for calcium oxide is. Then we can figure out what the constituent elements are. We can figure out their standard states and put it all together into a formation reaction. So for calcium oxide, if we remember our ionic formula writing efforts, we would put the calcium ion down and the oxygen ion down. We would see that one has a +2 charge and one has a -2 charge. So they will exist as 1-to-1 ratio ionic compound. So the formula, therefore, calcium oxide is CaO. All right. So Then we need to write a formation reaction. Formation reactions show compounds, CaO, being written from their elements at standard states. So the standard form, and I've got the entries from oxygen and calcium ripped from the thermodynamic tables here. And I see for calcium, the one with the zeros, the one at the top, is the standard state. The one with the zeros in the thermochemical data is always the standard state. So the calcium solid is the standard state of calcium. So I could say CaS is one reactant. And the standard state of oxygen is O2 gas. So I have to write, if I'm writing a formation reaction, I can't just put oxygen down. I have to put O2 gas down. So that's the start of the formation reaction for calcium oxide. However, we see that this is not balanced. I've got calcium solid plus 2 O2 gas yielding calcium oxide, but only one oxygen atom. Something disappeared here. So if I were balancing this as a chemical equation, the formation reaction would look like this: 2 and 2. 2 moles of calcium solid plus 1 mole of oxygen gas yields 2 moles of calcium oxide. However, if I remember, thermochemical data likes to show just 1 mole of product. So I need to figure out a number that I can divide everything by to get 1 mole of product. When I divide everything in that equation by 2, 1 divided by 2, 2, then I will have 1 mole of calcium solid plus a half a mole of oxygen gas yields 1 mole of calcium oxide solid, and that would be the formation reaction for calcium oxide. I could even take it a step further. If I look up at the calcium table, I see that calcium oxide is one of the listed elements, and it tells me what the enthalpy of formation is for calcium oxide in that table. And it says it is negative 634.9 kilojoules per mole. So I can say that this formation reaction here has a delta H of negative 634.9 kilojoules per mole. That isn't always the case. I don't always have that compound that I made in those tables, but it's a nice feature of these because we'll see how we can combine some of these to get new reactions that we don't have the data for. Here on this slide, we have another question. Write the formation reaction for K2HPO4. And we would start by figuring out what the standard state of all of the different elements that make up this element are, because they go ahead and give us the formula. We will figure out, I kind of take it for granted, you can look up the table yourself. You can, if you go and search for each element in there, you would see that the standard state of potassium is potassium solid. The standard state of hydrogen is H2 gas. The standard state of phosphorus, now I did put this one in the slide here because it may be the most different one we've seen yet. If we go to phosphorus's entry in that thermodynamic table, we'll see that the one with 0 kilojoules per mole as the formation energy is the P4 variant of phosphorus, and so that means that is the standard state of phosphorus is P4 molecules plus oxygen standard state, if you go and find the oxygen, is O2 gas. So each of those things would add up to form K2HPO4 in the formation reaction. And then of course you would need to balance everything to have the right amount. So if we said we had, and if you want to avoid having to divide everything and figure out how to get 1, just put coefficients now, and it's a little bit easier because you're allowed to put fractions. You can put whatever fraction you need to in front of the element to get the right number on the other side, because you're never changing that other side from 1. You can put any fractions you need to. So in front of the K, we'll need a 2. In front of the H, we'll actually need a 1/2, because that will give us a 1H essentially on the other side. In front of the 4, we'll actually need a quarter because that will give us 1P on the other side. A fourth of P4 is just 1P. And then for O2, we actually need 4 oxygens on the other side, so I'll have to put a 2 in front of it. So the formation reaction for potassium biphosphate is the name of that compound, is 2 potassium moles plus a half a mole of H2 gas plus a quarter mole of phosphorus plus 2 moles of oxygen gas gives us 1 mole of K2HPO4. And then if you go and look, you would actually see we don't have the enthalpy of formation for that compound in our thermodynamic table, so we don't know. We'd have to investigate to figure out. We'd have to do some calorimetry to figure out the heat of formation for this reaction. And that brings us to Hess's law. Hess's law says that because enthalpy is a state function, we talked about how state functions do not care about the way in which they arrived at their state. That means that we can write a reaction for which we do not have an enthalpy change for if we can break that reaction down into stepwise reactions, break it into smaller pieces that we do know the enthalpy changes of. The overall enthalpy change is the sum of the enthalpy changes of the stepwise reaction. Because it's a state function, it doesn't matter if that's how that system or that compound was actually formed or not. The energy changes associated are the same because enthalpy is a state function. So over the next few slides, we'll look at some applications of Hess's law and delta H in this manner. There's a couple of features that are important for keeping in mind while we do this. Delta H is directly proportional to the quantities of reactants or products. For example, the enthalpy change of the following reaction, giving us 1 mole of O2, has an enthalpy change of 33.2 kilojoules. However, if we had 2 moles of O2 produced, that would also multiply the enthalpy change by 2, since there's 1 mole in the first reaction, meaning that an enthalpy change of 66.4 joules would occur. In general, if we multiply or divide an equation by a number, the enthalpy change should also be multiplied or divided by the same number. Delta H for a reaction in one direction is equal in magnitude and opposite in sign from delta H for the reaction for the reverse direction. For example, given that the following the reaction says that 1 mole of H2 plus 1 mole of Cl2 forming 2 moles of HCl has an enthalpy change of negative 184.6 kilojoules. So if you were to turn that around and say 2 moles of hydrogen chloride gas decomposing into 1 mole of hydrogen gas and 1 mole of chlorine gas, the enthalpy change would be positive 184.6 kilojoules. So we see here on our first slide, our first application of Hess's law, where we're given an equation, PCl5 decomposes into PCl3 and chlorine, but we don't know the delta H for that reaction. We have some reactions, however, that will result in that equation if we can figure out how to combine them. And we do know the delta H's for those reactions. So if we can combine them in a way that we get the reaction that we want, we can get the delta H for that reaction. And so what we do is we actually add both of these reactions together. We can put all of the things on the reactant side, plus and plus and plus and plus, and then all of the things on the product side, plus and plus and plus and plus. And we can add similar terms together, and we can, if there are similar terms on either side of the arrow, we can cancel them out. And I'll show you what I mean here. So if we combine the two expressions that we have here, we have P4 plus 6Cl2. So we will say that P4 plus 6Cl2 yields 4PCl3. But we also see 4PCl5 in the second equation's reactants. And so we can put it in there with our reactants too, if we're combining the two processes. And then the products are P4 solid from the bottom equation, 10 Cl2s from the bottom equation, and 4 PCl3s from the top equation. Now we can do some cancellations. I see 1 mole of P4 on the reactant side and 1 mole of P4 on the product side. Because the P4 is used up in the process, we can cancel that out. I see, oh, that should be Cl2 there. I see, and it should be 6 moles because, there we go. I see 6 moles of Cl2 on the product side or reactant side, and I see 10 moles of Cl2 on the product side. So that means I can call that, that will cancel, and that will be 4 because it's like an addition. It's like algebra with the arrow being the equal sign. 6 on one side, 10 on the other leaves you with 4 on the one side after you do your cancellations. So, and that leaves me with both of my other reactants canceled out. It leaves me with just PCl5 in the reactant side, which is the reaction I'm trying to consider. However, it says 4 PCl5 yields, P4 has been canceled. My chlorines are now 4 Cl2s and 4 PCl3. You also have to add the enthalpy changes from those reactions together, just as we did with the compounds. So they will be negative 24 plus 999. So if you add 2439 kilojoules plus 3438 kilojoules, that is 999 kilojoules total for the reaction we have now represented. However, we know we probably can see that we're not quite done yet. The reaction we're asked to find is actually 1 mole of PCl5 decomposes into 1 mole of chlorine gas and 1 mole of PCl3. The reaction we've determined has that in factors of 4. It's pretty plain to see that we need to divide the entire reaction by 4 in order to bring those moles down to 1. And so when we do that, we also divide our change in enthalpy by 4. So we would just rewrite everything. PCl5 yields Cl2 plus PCl3. And the delta H is 999 divided by 4. 250, just about. 249.75. Delta H for this reaction is 249.75 kilojoules. We will do a few more examples on the next couple of slides. We've got another example here that says 2C2H4O in the liquid state plus 2H2O can give us 2C2H6O in the liquid state plus O2 gas. We don't know the delta H of this reaction, but we do have two reactions that we think might help us write one. We have C2H6 reacts with 3 moles of O2 to give us CO2 and H2O. We have C2H4 reacting with 5½ moles of O2 to give us CO2 and H2O. So one thing I notice here is that the reaction or the equation that we are asked to find the enthalpy for has a hydrocarbon, the C2H4O, and water in the reactant side. Neither of my given reactions have water in the reactant side. So if I add them together, I'm not going to end up with water on the reactant side. I may want to remember, though, at this point, they both have water in the product side, or yeah, they both have water in the product side. And I can rewrite these backwards if I so choose, as long as I change the sign of my change in enthalpy. So We also keep in mind that we want C2H4 to be in our reactant. So this is probably, the bottom reaction is probably not the one we want to turn around since it already had C2H4O in the reactants, and C2H6O wants to be in the products in this one. So the top reaction here is the one we're going to turn around and flip the sign for. So what I will do is I will rewrite that top one. I will say that 2CO2 plus 3H2O reacts to give us C2H6O plus 3O2, and the delta H is positive 685.5 kilojoules. Now I can add that to that bottom reaction. So with all of, if I kind of mark this one out so I'm not looking at it any longer, with all of those on one side, all of these on one side, on the reactant side, and then all of these on the product side, looks like this. C2H4O plus 5 halves O2 plus 2CO2 plus 3H2O yields 2CO2 plus 2H2O plus C2H6O plus 3O2, and the delta H is 685.5 plus negative 583.5. The delta H is 102 kilojoules. Delta H is 102 kilojoules. So then I'll cancel and maybe see if the reaction looks like I want it after cancellation. So C2H4O has nothing on the other side to cancel with. 5 halves oxygen has 3 oxygens to cancel on the other side. So 5 halves is not quite 3, so that one's going to cancel out. And 2CO2, but it will, well, we'll stay there. 5 halves oxygen is essentially 2.5, right? 5 halves is 2.5. So 3 is actually 6 halves. So we're left with 1/2 of oxygen over here. 5 halves canceled out of 6 halves is 1/2. 2 cancels with 2, and we will have 1 water left over here. The 2 waters will cancel out 2 of that water, so we'll be left with 1 water over there. All right, so now let's go ahead and look and see what our reaction looks like, because we don't have anything to cancel C2H6O out with. So rewrite everything I have left over. C2H4O plus H2O yields 1/2 O2 plus C6H6O with a delta H of 102 kilojoules. However, that's not quite right. I can see that everything in my equation that I've arrived at is about a factor of 2 off from how I want the equation. I guess they just want the moles, the oxygen to be 1 mole. So if we multiply everything by 2, we'll arrive at that. 2 moles of C2H4O plus 2 moles of H2O yields 1 mole of O2 plus 2 moles of C6H6O. And of course, we would need to multiply the enthalpy change also. So the enthalpy change for this reaction is 204 kilojoules. So this question says, find delta H for the reaction below given the following reactions and subsequent H values. We're looking for the reaction enthalpy for N2H4 plus CH4O yields CH2O plus N2 plus 3H2. So we don't know the enthalpy of that reaction, but they have given us some reactions we do know the enthalpy of. We got a couple of ammonia decomposition reactions and then a combustion with hydrogen reaction here in the bottom. If we want to get, we kind of want to pay attention to what we want to get into the reactant side and what we want to get into the product side. And we see for the reactant side, we want N2H4 and CH4O. None of these reactions here give me N2H4 or CH4O on the reactant side, so I know I'm going to have to turn around a couple of these problems. In fact, I'm going to have to turn around the top problem and the bottom problem in order to get the correct reactants in the right place. I need CH2O on the product side, which I will get by flipping this around. I need N2 on the product side, which I can get by just leaving this reaction as is. And I need H2 on the product side. Again, I can get that from leaving this reaction as is. So let's go ahead and flip the correct reactions we need to flip. All right, and now we have CH4O decomposes into CH2O gas plus hydrogen gas. And the delta H there is the opposite as of above since we turned the reaction around, which is negative 81.2 kilojoules. We have N2H4 plus H2 reacts to give us NH3. We pulled, that one was from above as well and turned around, the top reaction from the above as well and turned around. And then we have the reaction we didn't modify down on the bottom, 2NH3 yields N2 plus 3H2. So if we put all of our reactants on the reactant side and all of our products on the product side, this is what we come up with. We have CH4O plus N2H4 plus H2 plus 2NH3 yields CH2O plus H2 plus 2NH3 plus N2 plus 3H2. If we cancel the H2, the two H2 moieties we see, we would be left with what we see here. We also can cancel the two NH3 moieties on each side. And when we do so, we are left with this reaction, CH4 plus N2H4 yields CH2O plus N2 plus 3H2. That's exactly the reaction that we are looking for in the top equation there. And after adding out all of the delta H's of those three reactions, we get a result of negative 46.2. So this reaction this reaction here has a delta H of negative 46.2.
And after that discussion, it actually gets a little bit easier here at the end of the enthalpy discussion. So because enthalpy is, as we say, that state function, it turns out that you can determine the change in enthalpy for any reaction if you know the enthalpy of formation of all of the products and the reactants. So if you can look down your thermodynamic table there and find each of the products and each of the reactants for a chemical reaction listed, then you can determine the overall change in enthalpy for that reaction by this equation, which is probably a little bit more complicated or a little bit less complicated than it looks. So what this equation, all it says is you add up all of the enthalpy of formation of their products multiplied by their respective molar quantities, and then you subtract from that all of the enthalpies of formation of the reactants times their respective molar quantities. We will look at a few of those examples on the next slide. And we have our examples here on this page. We can see we have a couple of reactions here. We're interested in knowing the change in enthalpy for these reactions. So we can do it the easy way. If we go and see, are all of these species represented in our enthalpies of formation table? And it turns out they are, so we want to list the enthalpies of formation for each of the species underneath them so that we can keep them noted. So I would use the thermochemical information table to get each of these enthalpies of formation for the species. Then I make sure to multiply them by the molar quantities from that respective equation. We can see the molar quantities appearing there in front of their boxes. So we just pull the molar coefficient straight from the equation and put it in front of that enthalpy of formation. Then we multiply those and add them together. So where these showed up down here, those are where those brackets are. Those figures are summed together, added together after they are multiplied, and you see the results pop up underneath them. And so we have a reactant side and a product side, and a reactant side and a product side. And the Hess's law says that the enthalpy of the reaction is the products minus the reactants. So if we set out our products minus the reactants, we would see that the enthalpy change for the first reaction is 1615 kilojoules. The enthalpy change for the second reaction is 550.83 kilojoules. And the enthalpy change for the fourth reaction is negative 427.23